Hello everyone, my name is Gabriel Stylianidis and I would like to welcome you to this professional development session of the teaching and learning of fractions. Although the focus of this session is on fractions, we will also consider broader issues about the teaching and learning of mathematics related to task design and also to engagement in mathematical practices such as mathematical reasoning and problem solving. Fractions constitute an important part of the school curriculum and relate to many other notions such as decimals, ratio, proportion, and so on. Children start learning about fractions from the early years and develop their understanding throughout the primary school curriculum and beyond. Because fractions is a domain that causes children many difficulties and misconceptions, many secondary school students have difficulties in this area as well. So this session is designed to be useful as a CPD to primary school teachers, no matter which year group they teach. Ideally, this will be done as a whole school CPD, but at least 2 teachers should do this session together so that they have an opportunity to discuss and share ideas with each other. So before we begin, I would like to offer some general information about the session. Although this is a pre-recorded session, it is designed to be interactive. So what I mean by that is that I will be asking you at certain points to think about a problem or a question before you move on with the video. Based on my experience teaching face-to-face different versions of this session to both primary and secondary teachers over the years, I will try to anticipate some common responses or issues you may face, and I will provide step-by-step input to help you progress in your thinking. This session will use tasks as mediating tools. Specifically, through engaging you in a mathematical problem, I will aim to promote reflection on your own mathematical activity and also on pedagogical implications of this activity. An important suggestion I have for you for this session is that even if a task I will ask you to engage with on the surface may look purely mathematical or purely pedagogical task, there is value in your work on them to not limit your thinking to mathematical or pedagogical issues respectively. Rather, it will be beneficial to explore issues that the task can raise in the interplay between mathematics and pedagogy, and I will aim to help you with that. So finally, and during the session, I will provide a couple of references in case anyone is interested to delve deeper into relevant issues. And this is a paper that discusses and exemplifies some of the ideas I just described about the interplay between mathematics and pedagogy in teacher education. Okay, moving on now to an overview of the session. First, we will work on a mathematical problem, which I call the cupcake problem. And then we will consider the mathematical and pedagogical ideas involved in our work on the cupcake problem and also their applications and implications for your practice. And the third part of the session will be to engage in task design and modification while keeping the target mathematical content the same. So I hope all of these will make more sense to you as we go along. So starting now with the cupcake problem. So this is the problem. I will read it quickly. For his party, Alex bought a cupcake party platter that contained a variety of cupcakes. At the party, Bob ate a third of the cupcakes because he had skipped lunch. Then Caroline came by and ate a quarter of the remaining cupcakes because she really liked them. Dan ate 2/3 of the cupcakes that were left. Then Eva ate 1 cupcake as she was leaving the party, and finally when his guest left, Alex noticed there were only 2 cupcakes remaining. And these are the questions that I would like you to consider. How many cupcakes were on the party platter to begin with? How many cupcakes did each person eat? And I'm also asking you to solve the problem in different ways, as many different ways as you can, and then try to order these different ways in terms of their difficulty or level of sophistication. So before I ask you to work on these questions, I would like to make a few comments that will connect this slide to ideas I mentioned earlier about the general information about the session. So working on this mathematical problem is a way to experience for yourselves at your own level something of what your students might experience in the classroom. The problem is not meant to be one that can readily be used in the classroom, even though it is certainly adaptable to the school context, as we'll discuss in the third part of this session. Specifically, although the problem relates to a key topic of the primary school curriculum, the expectations in the problem of producing multiple solutions and ordering them in terms of their difficulty, for example, make the problem appropriate for teachers. As I mentioned earlier, it will be useful for you as you work on the problem to also be thinking about how your mathematical work may give you insights into your teaching. Okay, so I would like to ask you now to please take at least 5 minutes to think about the problem individually, and then at least 10 additional minutes to discuss your ideas with your partner and to share ideas with each other and strategies. Okay, now please pause the video, and as I mentioned earlier, for 5 minutes individual work and 10 minutes with the work with a partner and work on the problem. Thank you. I hope you enjoyed your work on the problem thus far. One strategy that people frequently use as an initial strategy is to guess and check. Although it is not the most efficient strategy, it still offers one way to approach the problem. Also, one could find ways to not make random, but rather reasoned guesses of numbers to check. What I would like to do next is to give you 2 hints for 2 additional solutions to the problem. If you haven't explored these approaches yet, please pause the video again after I show you the 2 hints and try them now. So the first hint is to try and work backwards. Why does working backwards offer a meaningful strategy to approach this problem? So this is something for you to consider if you haven't already. And the second is to try and represent the cupcake platter with a geometric figure. What figure will you use? So this is something for you to think about, and also whether that would make a difference. Okay, as I mentioned earlier, please pause the video again and try and work these 2 additional ways of approaching the problem if you haven't already. Okay, let's go through together now a working backwards solution first. Working backwards makes sense in this problem because the only concrete numbers that we get in the problem are provided at the end of the problem. We have 2 cupcakes that were left, plus 1 that Ava ate, which makes 3 cupcakes after Dan ate his piece. So now, if we see the green highlighted part, that is the same as if we had to solve the problem that said after Dan ate 2/3 of the cupcakes, 3 cupcakes were left. How many cupcakes were there before Dan? So 3 cupcakes represent 1/3 of the cupcakes before Dan. So before Dan, there were 9 cupcakes. We can then use this information to move further up in the problem to the new highlighted piece. So here we have, we could replace the highlighted part of the problem with the problem at the bottom of the slide. After Caroline ate 1/4 of the cupcakes, 9 cupcakes were left. How many cupcakes were there before Caroline? So 9 cupcakes represent 3/4 of the cupcakes before Caroline. So before Caroline, there were 12 cupcakes. So as you can see, the whole is changing. We have a changing whole because after each person eats their piece, we have a different number of cupcakes. So the fractions refer to the new whole we have at each time. We can move on now to the next bit in the problem that says that about Bob. And that's as if we had to solve the problem. After Bob ate a third of the cupcakes, 12 cupcakes were left. How many cupcakes were there before Bob? 12 cupcakes represent 2/3 of the cupcakes before Bob. So before Bob, there were 18 cupcakes. We can now use this number to go back and figure out how many cupcakes each person ate in the problem. So that was one way to solve the problem. I also mentioned earlier about the guess and check strategy that would offer another way to solve the problem. If we go now to hint 2, about drawing a figure, a geometric figure, that would help us solve the problem in other ways as well. So when we're dealing with fractions, we are often very used to thinking about pizzas and circles. In this problem, representing the whole with a circle would not be the most useful representation, as we will see in a minute. Indeed, one idea to keep in mind is the issue of different representations, which can be appropriate in different solutions. Children may feel comfortable with a particular representation, but it's also useful for them to have a range of possible representations at their disposal and use each of them whenever it's more appropriate. So here on the flip chart, I drew the two common geometric representations one would use, the circle and also rectangle. And as I mentioned earlier, in this particular case, the rectangle would be an easier representation for us to use. So I will start from that. So the problem said that Bob ate a third of the cupcakes, and each of those figures represents the whole platter. So if Bob ate a third, so we need to split the platter into 3 parts, and one of those would be Bob's. So this is how much Bob ate. Then the problem says that Caroline came by and she ate a quarter of the remaining cupcakes. So we need to split the remaining 2/3 into 4 parts so that we can give one of them to Caroline. So Caroline is going to eat one of these 4 left over after Bob ate his piece. So then the problem says that Dan ate 2/3 of what was left after Caroline ate her bit. So we need to give to Dan 2 of the 3 remaining pieces. So let's say this is Dan's. And then the problem says that Eva ate 1 cupcake and there were 2 cupcakes left. So we know that what's left is 3 pieces. So 3 pieces correspond to half of a third of the whole platter. That means a 1/6. So 1/6 is 3 pieces. The whole platter would be 18 pieces. And then we can go back and see how many cupcakes each person ate. So if we were to use the circle, in order to draw the thirds to begin with, in order to assign Bob's part to him, we'd need to think about how many degrees are in a circle and then divide it by 3. So that would be 360 degrees for the whole circle. So we need to divide it into the 3 parts, roughly 120 degrees. So that would be So we're doing the same thing we've done here, but dividing the circle into 3 parts, and this part will be Bob. Then, to find Caroline's bit, she ate a quarter of what was left. So that means we need to divide the 2 remaining pieces, split each of them into half, so that we can get the quarter. So each of these bits now is 60 degrees. This part is 60 degrees as well, and then here and here. So for Caroline, let's say we want to give her this part here, because she had a quarter of what was left after Bob. And then we're moving on to Dan, who ate 2/3 of what was left after Caroline ate her piece. So we can give to Dan 2 of the remaining 3 pieces. So let's say we give to Dan this one and this one. And now what was left after Dan is the 3 pieces, one that Eva ate and the 2 remaining cupcakes that would be into this last section there, which corresponds to 60 degrees, because remember we split the third into half, so this is 60 and this is 60. So 3 cupcakes correspond to 60 degrees, that's 1/6 of the circle, so the whole circle corresponds to 18 cupcakes. It might be useful to point out here about the circle representation that even though I referred and I used the degrees, it may not be necessary for one to do that. One could try and divide the circle into 3 parts to begin with, and then divide the 2 remaining parts into, split them into half in order to find Caroline's bit. It's just like doing that is harder than in comparison to the rectangle representation. And if you don't draw the figure accurately, then that may cause some more difficulty. But it's also possible for one to do it in the same way as in the rectangle without having to worry about the degrees. So both of these figures, we can see, for example, that Bob and Dan ate the same amount. Consider this part and this part are the same, both 1/3 of the whole, and here as well. This is Bob's piece and this is Dan's piece. They each ate 1/3, and we can also see that Caroline ate the same amount that was Eva and the remaining cupcakes, which is 3 cupcakes, or she ate half of what Bob and Dan, and we can see it here as well. So these 2 representations, we can see how they correspond to each other, and also one possible way to help us approach the problem. So in addition to these solutions, there are many other ways that one could do it. One could design a table, for example, and then have how many pieces each person ate and what was left after that person, and then go down the table in a systematic way, or use the information in the problem to devise different algebraic equations. So you don't have to consider those solutions, but for anybody who is interested, we have uploaded a separate handout with these solutions that you can refer to if you wish. Now that we've discussed different solutions, let's go back and consider the question that was asking you to order different solutions in terms of their difficulty or level of sophistication. The difficulty or level of sophistication depends on the children, on the students who worked on the problem. The way in which I discussed the different solutions could possibly constitute one way of ordering them based on their difficulty or level of sophistication. So I mentioned first the guess and check strategy, then we worked on the backwards solution, and then we discussed the 2 geometric solutions, starting with the rectangle and then going to the circle. And also, as I mentioned earlier, there are also other solutions that we could have discussed next that involve drawing a table and coming up with different algebraic equations. So the real aim, though, behind this question was to raise awareness of the importance of thinking about the order of solutions in the classroom. So let's imagine that we're all here together in this room at Oxford and we're working on the problem. And when we started sharing our different approaches and solutions, we started from some of the solutions that you can find on the handout about using algebraic equations, for example. Would that make a difference, perhaps, to some of the participants? So starting from solutions that more participants would likely relate to and understand could help us gradually move to more sophisticated solutions. And also pointing out the correspondences between the less and more sophisticated solutions could also help more participants understand solutions that they didn't use themselves to begin with. So the same ideas, of course, would apply for children. So I'm not suggesting here that solutions should always be presented in increasing levels of difficulty. Rather, my point is that it's important and useful for the teacher to consider how they want the sharing to happen and what implications might that have for their children, and to plan accordingly. Some of you may be thinking now, let's say that we want to present the solutions in a specific order. How can we facilitate that? Children could solve a rich problem in different ways. When we ask a child to share a solution, we could get anything from that child. We don't have much control. So please take a few minutes to think about this prompt and discuss with your partner if there are any strategies that you could use in order to have more control when you try to orchestrate these whole group discussions and sharing of student solutions. I hope you are able to come up with some strategies that can help you orchestrate strategically whole group sharing and mathematical discussions. One strategy I use when I implement this session face-to-face with teachers is to circulate around the room as they work on the problem and write down names of individuals or groups which came up with certain solutions. So the fact that as part of my planning, I have already put together a list of possible solutions that I want to make sure when discussing the whole group, it makes it easier for me to recognize a particular solution when I see it. So when it comes to sharing, I can ask certain individuals to share specific solutions that I know they have come up with and they have thought about, and I can be strategic in the order I choose those individuals. For example, I could say, John, would you please come up and share with us the solution that used the rectangle, for example. So a similar strategy could be used in the classroom with children. Orchestrating productive mathematical discussions is difficult for all of us, and I would strongly recommend this reading which discusses and breaks down this complicated process into 5 practices, which can be accessible even to beginning teachers. We'll now move on to the second part of the session, which is to try and bring together some of the mathematical and pedagogical ideas I already mentioned in the first part. So before I share some thoughts with you, I would like to ask you to pause the video and take a few minutes first to think together with your partner about specific mathematical ideas and pedagogical ideas that were involved in our work on the cupcake problem thus far. Okay, let's begin now with the mathematical ideas that were involved in our work with the cupcake problem. From my previous experience, these points are ones that participants are likely to think first in response to this question. So the importance of the unit or whole in interpreting fractions, the meaning of fractions as representing a part of a whole relation, and also the notion of changing whole in fractions, which was particularly relevant for the cupcake problem when we had different people eat a fraction of different cupcakes that were left in the platter. So these are all valid points and relate to the mathematical content that was addressed in the problem and in our work. Some people may think that our work on the cupcake problem was only about fractions, but it actually involved much more than that. We're often used to thinking when we teach about the mathematical content, fractions, decimals, and so on. And mathematical content is an important aspect of learning mathematics. However, learning mathematics is not just about the content. It's also about mathematical practices, such as problem solving, mathematical reasoning, representing ideas, making connections, and so on. And mathematical reasoning and problem solving are also strands in the mathematics national curriculum, as you know. So helping your students to understand mathematical practices is equally important to helping them understand mathematical content, because practices are at the heart of doing and knowing mathematics and are also applicable across all mathematical topics. So I'm going back now to our work on the cupcake problem. In no particular order, in our work on the problem, we engaged, for example, in representing the problem in different ways. It might be useful to ask ourselves, why was that important to do? Some children in the classroom will solve a problem, any problem, one way, and other children will solve it a different way. So exploring correspondences and connections between different solutions will help the children to better understand one another's solutions, because they will be able to connect it with how they've thought about the problem. We also discussed different problem-solving strategies. We mentioned the guess and check, the working backwards, drawing a figure, and we explored two different figures, one with a circle and another with a rectangle. And I also mentioned to you earlier that there are other ways to approach the problem, such as making a table and forming different algebraic representations and equations that you can find in the handout that I mentioned earlier. And also mathematical reasoning and proving. We had to explain our thinking convincingly why a particular answer was correct. And also, if this was a live session, we would have an opportunity to explore other solutions and also solutions that perhaps had some incorrect features into them, and explain why those solutions were incorrect. So one question that may come to mind here is the following. The cupcake problem is an example of a very rich mathematical problem, and there is so much one could do with it and learn from it. How much time, though, should a teacher spend on a single problem, not necessarily the cupcake problem? So I invite you to think about this question next, which will naturally lead our discussion to the pedagogical implications from our work in the session thus far. So please pause the video for a few minutes now and discuss this question. So some ideas about this question. If the problem is rich and the teacher is going to use it to achieve several different goals, then it might be worth spending a significant amount on the problem. However, a rich problem is by itself not enough in order to generate this rich mathematical activity and learning. A teacher is the one who is going to make that happen, and a teacher needs to have clear goals in mind when implementing a rich problem in the classroom. So, for example, before teaching a session like the one that we discussed today, I would make sure that I'm clear what I want to achieve, certain solutions that I would like to make sure that we discuss, certain connections, ideas, or points that I would like to highlight and raise in the discussion. So as teachers, if we are clear about our goals in using a problem, and if we want to use the problem to achieve multiple aims, then spending more time on it than usual problem might be time well spent. So moving on now to other pedagogical insights from our work on the cupcake problem. The first one we've already talked about. It's about the importance of preparation and having clear goals when implementing a rich problem. Another important pedagogical idea that derives from all the different ways we solve the cupcake problem is that it is possible to set up a problem that can be accessible to students of different levels. And so the cupcake problem can be seen as an example of a problem that can be used for differentiation by task. So all students being able to start working on a problem in some way is important, especially in classrooms with mixed ability students. So the selection of the problem can offer one possible way to productively engage a diverse group of students. So indeed, differentiation doesn't necessarily mean more activities, but can also mean different ways of approaching the same problem and going into more depth. So an advantage of having all students work on the same problem is that during the sharing of the solutions, all students will then be able to benefit from each other's work. So this wouldn't necessarily be true if different students worked on different problems, because those students who didn't work on a particular problem, it wouldn't be easy for them to follow what the other students have done. So a third idea that you may have thought about is the importance of having a repertoire of multiple representations. And we've seen that when we discuss, for example, the two different geometric representations for the problem. Another point relates to thinking about the ordering of solutions and implications these may have on students' learning and engagement, as we discussed earlier. And the previous point fits nicely into the broader issue about strategies for orchestrating productive mathematical discussions, such as circulating around during small group work and identifying students to share certain solutions rather than doing it in a more random way. And once again, I remind you about the paper by Stein and her colleagues, which I think you will find very useful. I'm sure there is also other things that you came up about pedagogical insights that you gained. I have only highlighted here some points that I considered important. Moving on now to the last part of the session, which will be to use the cupcake problem as a context to practice a skill that is important for teachers in all topics they teach, namely task design and modification while keeping the target mathematical content the same. And I will start from the last thing I mentioned, which is to clarify what I mean by keeping the target mathematical content the same. So for example, if a teacher has the cupcake problem and was to modify it to make it easier or harder, while keeping the mathematical content the same, that would mean that the new problem can't be a problem that simply relates about fractions. It has to be a problem that focuses on the part-whole interpretation of fractions and the notion of changing whole, which, as we discussed earlier, are key content targeted by the cupcake problem. So in what situations might a teacher need to do that? Might need to engage in designing or modifying an existing task while keeping the target mathematical content the same. So you may want to pause the video again here and just have a think with your partner about possible situations where these might be needed. Welcome back, and some thoughts from me about situations that this skill, this activity might be useful in teaching. Relate, for example, when say that you work with your students on a problem and then you wanted to design a new problem as practice, or to see whether the children in your classroom understood the ideas in the original problem. So in this situation, you may want to design either a new problem of similar difficulty or slightly harder maybe. Another example may be that you found a problem in a textbook or online or in a CPD course like this one, and you like the problem and the ideas in it, but it's too hard for your students. And the cupcake problem could be one such example. So here you want to design a new problem, but that will be more appropriate for the level of your children, that will have to be less challenging. A third example might be that last year you taught a year 2 class, and this year you're teaching a year 3 class, and you have a problem that you used last year, but a slightly more challenging version would be more appropriate for the new group of children that you're teaching this year. So in this case, you would need to modify the problem to make it harder, but while at the same time keeping the ideas the same. So there may be more examples that you have come up already, but I hope this gives you a sense of where this skill might be useful in your practice. So the next thing I would like to ask you to do is, together with your partner, to try and modify the cupcake problem to make it easier or harder while keeping the target mathematical content the same. And also to think about what makes each of your problems easier or harder than the original problem. And once you do that, I would also like to invite you to reflect about if there are any general ways that you could extract from this work in which a problem can be made easier or harder than a given problem. So please pause the video now and spend some time on this activity. Okay, let me now briefly discuss and illustrate some strategies to make a problem easier, illustrated in the context of the cupcake problem. And even though I will present those strategies one by one in an isolated way, it's also possible to think about combination of strategies. So a first strategy would be to use easier numbers, or numbers that can make a solution easier. So this would be one example. So this is the original problem, and I replaced the fractions, which I highlighted, so that it will be easier for you to spot them. So if you try to use these fractions, these new fractions, with and follow the rectangle geometric solution, you will see that the solution will become very straightforward. So this would be one example. A second strategy would be to use fewer steps in a problem. So there are quite a few things happening in the original problem, but it doesn't necessarily have to be that way. So this would be an example where we have fewer people involved in the story and fewer steps. So you may want to pause the video, read the problem, discuss it with your partner before you move on. A third strategy would be to give the numerical information at the start. So as you remember, in the original problem, the concrete numbers we got at the very end of the problem. So if we started with a concrete number, then that would make the problem much easier. And again, like on the slide, you can find one example of this strategy. And the final strategy that I would like to share with you, and this is not an exhaustive list, this is just some ideas from me that I chose to share with you, but I'm sure you may have come with other ideas as well. The last thing is to make the problem less wordy. So you may have felt when you're reading the problem originally that actually there are lots of things that could be taken out and the problem to still stay the same. But that would be an example of how one could simplify the problem in terms of the wordiness and thereby make it easier for someone who tries to solve the problem to identify the key information. Okay, moving on now to strategies to make a problem harder. One could think of the opposite of the strategies that I shared earlier that were intended to make a problem easier. Another idea is that if the children have already solved a particular version of the problem, a harder problem could be one in which some of the original strategies, or maybe one of the strategies that most of the students used, would not be applicable or would be in need of modification. And here is an example of that. So for his party, Alex bought a cupcake party platter. At the party, Bob ate a third of the cupcakes. Then Caroline came by and ate 2 cupcakes. So here we have a concrete number in the middle of the problem. And then Dan ate half of the cupcakes that were left. When his guests left, Alex noticed that there were 5 cupcakes remaining. So arrange the numbers so that the answer will always remain the same. But here gives you an idea of how, for example, the geometric figure would not work as in the original problem. And that would make the problem harder for anybody who tried to solve it. This brings us to the end of the session, and here are 2 final questions for you to consider and discuss with your colleagues. What stood out to you from the session, and what ideas do you think you may be able to take to your teaching? And before we close, I would like to leave you with one final thought that you may want to consider in this final set of reflections. Although the particular mathematical content this session focused on was fractions, most of the ideas we explored pertained to mathematical topics and teaching and learning mathematics more broadly. So this might be something useful for you to consider. Thank you very much.